Hello everyone, welcome to the channel. In our today's video, we will be discussing some important theorems in calculus which are in our syllabus. These theorems will include the derivations of mean value theorems and some other theorems. Let us take a look at what all theorems we will be covering today. The theorems covered in today's class are Fermat's theorem, Rolle's theorem, Lagrange's mean value theorem which I will be writing as LMVT, Cauchy's mean value theorem which I will be writing it as CMVT in the later. Also, we'll be discussing about Taylor theorem and at last Darboux theorem. The Darboux theorem is not really very helpful in our present problems, but its proof will be very helpful because it will be like a learning test. You can try it in the end of the video. But now, before we start, let us look at two of our fundamental theorems. Though even these theorems can be proved, their proof is out of our syllabus. So today we'll treat these two theorems as our fundamentals and we'll prove the others using these. The first theorem is intermediate value theorem. This intermediate value theorem is true for every continuous function in a domain A and B. Intermediate value theorem says there exists a C belonging to A comma B such that for every U belonging to f of A comma f of B, f of C is equal to U. You can also see from the graph that if we take a U in between f of A and f of B and then we project it on the graph, we can see that there will always exist an x coordinate, which is all that intermediate value theorem is trying to say. Let us move on to our next theorem, which is extreme value theorem. It is also true for every continuous function. Let's first define small m as the minimum value and capital M as the maximum value, such that for all x belonging to A comma B, f of x lies in between small m and capital M, where small m is less than or equal to capital M. Let me explain. For suppose you consider this graph in between the points A and B. Not only this graph, any graph. We'll always find a minimum and maximum for this graph is what extreme value theorem guarantees. Here I wrote that small m is less than or equal to capital M. This equality case holds when the function is a constant function. Also note that I put closed intervals A comma B, which means that these minimum and maximum values can be attained even at the boundaries, not only in the between. I hope everyone understood. Now let's move on to our theorems. Today, first we will be proving Fermat's theorem. Fermat's theorem for Fermat theorem, we will be defining a function h such that it is continuous in closed interval a comma b. It is differentiable in open interval a comma b, where a comma b belong to R, and let's say b is greater than a without loss of generality. This definition will be common even in the upcoming theorems that we are going to derive. It's very important. In Fermat theorem, we claim that if C belongs to A comma B is a point of extrema, then h dash of C is equal to 0. See that I have put an open interval A comma B, not a closed interval A comma B, because we know about the function's differentiability in open interval A comma B. We can't exactly comment about it at the boundary points. And also many of you will think that we know that at the point of extrema and minima, at the point of maxima and minima, the slope of derivative is 0. But today let's see how we can prove it using the first principle of derivative. Let's do one thing. Let C comma h of C be a point of extreme or extrema, where C belongs in open interval A comma B. Without loss of generality, let's say h of C is a maximum value. Even for the minimum value, the logic will be same. So let us focus on what happens if h of C is maximum. If h of C is maximum, then we can say that h of C is greater than or equal to h of x for all x belongs from A comma B, which implies that h of C is greater than or equal to h of C plus h, where let's say h is a greater than 0 quantity. And so we were that this h is just a scalar quantity, it's not any function. H is greater than 0. This means that h of C plus h minus h of C is less than or equal to 0. If I divide with h on both sides, since h is a greater than 0 quantity, the inequality sign will not change. Now what I'll do is, I'll take limit h tends to 0. Since h is a greater than 0 quantity, I'll tend it to 0 plus. Limit h tends to 0 plus h of c plus h minus h of c divided by h is less than or equal to 0. From first principle of derivative, we know that this thing is nothing but h dash of c. H dash of c is less than or equal to 0. Let's call this our inequation 1. Now we can also look at this in the other way. We can say that h of c is greater than or equal to h of c minus h. C minus h is nothing but a point which is on to the left side of c. Now what I'll do is, I'll again take h of c to the RHS. H of c minus h minus h of c is less than or equal to 0. This time what I'll be doing is, I'll be dividing with a minus h, since I have a minus h here. Since I divided, since h is a greater than 0 and I put it minus h will definitely be a negative quantity. Now if I multiply negative quantity on both sides, the inequality sign must shift to the other side. It will be greater than or equal to 0. Now what I'll do is, I'll again limit h to 0 plus h of c minus h of c divided by minus h is greater than or equal to 0. This implies that h dash of c is greater than or equal to 0. This is our inequation 2. Now from inequations 1 and 2, we can say that 0 is less than or equal to h dash of c is less than or equal to 0, which will automatically imply that h dash of c is equal to 0. This is essentially the proof of Fermat theorem, though not very rigorous, where c belongs to open interval a comma b. You can also take h of c as a minimum value and try on your own. The logic will be the same. Now let's move on to our next theorem, which is Rolle's theorem. Now again we'll be using the same definition that we have used in the Fermat theorem. We'll define the function h such that it is continuous in closed interval a comma b. It is differentiable in open interval a comma b, where a comma b belong to R and b is greater than a without loss of generality. But in Rolle's theorem, we will be adding another additional condition which says h of a is equal to h of b. Our claim is that there exists at least one c belong to a comma b such that h dash of c is equal to 0. Now since we already proved Fermat theorem, this proof can be done in 3 to 4 lines. Now here we will be taking cases. Case 1. Let's say h is a constant function. This means that h dash of x is equal to 0 for all x belong to a comma b. This will automatically imply that h dash of c is equal to 0 where c belongs to open interval a comma b. Now let's take the other case. H is not a constant function. Now what we'll do is, since h of a equal to h of b is given and h is not a constant function, then from extreme value theorem we can say that there will exist at least one point c belong to a comma b such that h of c comma h of c is a point of extreme. And from Fermat theorem we already saw that the derivative at any point of extremum, if the function is differentiable, is h dash of c is equal to 0 from Fermat theorem. So in each of the two cases you can see that h dash of c is equal to 0. Therefore this will prove our Rolle's theorem that there will always exist a c belong to a comma b such that h dash of c equal to 0 provided h of a is equal to h of b. Now let's move on to our next theorem, LMVT, which is nothing but Lagrange's mean value theorem. Now again we'll be using the same definition. Define the function h such that it is continuous in closed interval a comma b. It is differentiable in open interval a comma b, where a comma b belong to R and b is greater than a. Claim is that there exists at least one c belong to a comma b such that you can also read it as h dash of c is equal to h of b minus h of a divided by b minus a. Whatever function you like, you can define. Now, in order to prove this theorem, we'll use Rolle's theorem. In order to use Rolle's theorem, we'll define a new function. Let's say g of x is equal to h of x minus h of b minus h of a by b minus a into x. Now if I put a in place of x, I get g of a is equal to h of a into b minus a minus h of b minus h of a into a divided by b minus a, which will give me that b times h of a minus a times h of b divided by b minus a. Now if I plug in b in place of x, I get g of b is equal to h of b into b minus a minus h of b minus h of a into b divided by b minus a. Now again on simplifying this, I will get minus a times h of b plus b times h of a divided by b minus a. We can see that these both quantities are one and the same. This will imply that g of a is equal to g of b is equal to g of b. Now we know that since h of x is differentiable in a comma b and x is also a differentiable function, we can say that g of x is also differentiable in a comma b. Now since g of x is a differentiable function in a comma b and g of a is equal to g of b, from Rolle's theorem we can say that there will exist c belonging to a comma b such that g dash of c is equal to 0. Let's see what is g dash of x. G dash of x is h dash of x minus h of b minus h of a divided by b minus a. Now if I plug in c, this g dash of x term will vanish. I will be left with h dash of c is equal to h of b minus h of a divided by b minus a, which is what we were required to prove, which is h dash of c is equal to h of b minus h of a by b minus a. Now let's move on to our next theorem. It is Cauchy's mean value theorem. Now we are using the same definition, but this time we are using it on two functions. Define the functions f comma g such that they are continuous in closed interval a comma b. They are differentiable in open interval a comma b, where a comma b belong to real numbers and b is greater than a without loss of generality. Here our claim is that there exists at least one c belong to a comma b such that f of b minus f of a by g of b minus g of a is equal to f dash of c by g dash of c. This looks very familiar to Lagrange's mean value theorem. Some people also think that let's apply Lagrange's mean value theorem separately on the function f and then separately on function g, and then we divide both the LMVTs to get this, which is absolutely wrong. Let's say if you apply Lagrange's mean value theorem on the first function, you are getting f dash of c1, and if you apply LMVT on function g, let's say you are getting g dash of c2. How can you guarantee that c1 will be equal to c2? You can't. That's why we'll be using a smarter approach. Again, similar to LMVT, we'll define a function. Let's define h of x is equal to f of x minus f of b minus f of a divided by g of b minus g of a times g of x. Now I will put in x equal to a. H of a is equal to f of x into f of a into g of b minus g of a minus g of a into f of b minus f of a divided by g of b minus g of a, which will give us that uh, f of a into g of b minus g of a into f of b divided by g of b minus g of a. Now let me do another thing. I'll put in x equal to b. H of b is equal to, which will again give us minus f of b into g of a plus f of a into g of b divided by g of b minus g of a. We can again easily see that these both quantities are one and the same. Again, we can say that h of a is equal to h of b. Now, since we defined f and g to be completely differentiable functions in open interval a comma b and continuous in closed interval a comma b, we can say that even h of x will follow the same property. Now, since h of a is equal to h of b, from Rolle's theorem, we can say that there exists c belongs to a comma b such that h dash of c is equal to 0. Now, if I take derivative and put in c in place of h dash of x, the h dash of x will vanish and I'll get that g dash of c into f of b minus f of a by g of b minus g of a is equal to f dash of c, which will prove our result f of b minus f of a divided by g of b minus g of a is equal to f dash of c by g dash of c, where c belongs from a comma b. Now here, if you notice, if I put g of x as some linear function, let's say ax plus b, g dash of x is nothing but a and g dash of c will also be a. If I put it in this equation, I get f of b minus f of a divided by b minus a times b minus a is equal to f dash of c divided by a. Now if I cancel the a on both sides, I get f of b minus f of a by b minus a is equal to f dash of c, which is nothing but our Lagrange's mean value theorem. Now what's so special about Lagrange's mean value theorem? Lagrange's mean value theorem geometrically means that if I consider any function, any differentiable continuous function in a bounded interval a comma b, here f of b minus f of a by b minus a represents the slope of a secant joining these points a and b. Now this theorem guarantees us that there will exist at least one point c such that if you draw a tangent to this graph at that point, the secant and this tangent will be parallel, which is the slopes of both of them are equal. Now let us move on to our next theorem. Now let us discuss about Taylor theorem. In this, we will define the function f such that it is continuous in closed interval a comma b. It is n times differentiable in open interval a comma b, and f dash f double dash till n minus 1 derivative of f are continuous in closed interval a comma b, where a comma b belong to R and b is greater than a without loss of generality, where n is a natural number. Our claim is that consider a base point b. If we know that about every detail of f at that point, like we know about the first derivative, second derivative, third till the nth derivative, then for any other x, we can write f of x is equal to f of b plus f dash of b into x minus b by 1 factorial plus so on till f of n minus 1 derivative of b by n minus 1 factorial into x minus b power n minus 1 plus n derivative of f at some point c into x minus b power n by n factorial, where c is some point which will definitely belong in between b and x. Now you may ask, why would someone even dream of a function like f of b plus f dash of b into x minus b by 1 factorial plus so on? I will give you a slight glimpse, but I will not go too deep into it. You can write f of x is equal to f of a plus integral from a to x f dash of t dt. Now what we can do here is we can repeatedly apply by parts to this integration, and we will see that the terms which you saw before will be appearing on the screen. And then when we come to the n derivative, we can use the generalized mean value theorem on that integral sign to get our derivative of f at c into x minus b power n by n factorial. But I'll not be doing it since I have not discussed generalized mean value theorem. Today we'll be solving it using Rolle's theorem. Now let's just ignore this part and continue. Let's define a function g of x is equal to f of x minus f of b plus f dash of b into x minus b, so on till f n minus 1 into b into x minus b whole power n minus 1 divided by n minus 1 factorial plus n derivative of f at c into x minus b whole power n divided by n factorial. Wait, let's write this as some quantity k, and in the end we'll prove that this k is equal to n derivative of f at c. Now since we are defining f of x equal to this quantity at every point of x, we want g of x to be 0 for all x. If we put b in place of x, we get g of b is equal to f of b minus f of b is 0, and in the remaining terms when we put b, the x minus b terms will go to 0, leaving us a g of b equal to 0. And we also want g of x to be 0 for all x belonging from a to b. Now here we can apply Rolle's theorem on g and say that there will exist c1 belonging in between b and x such that g dash of c1 is equal to 0. Now we can write g dash of x is equal to f dash of x minus f dash of b plus f double dash of b into x minus b plus so on till n minus 1 derivative of b divided by n minus 2 factorial into x minus b power n minus 2 plus k times x minus b power n minus 1 divided by n minus 1 factorial. Now if I substitute b again in place of x, I get f dash of b minus f dash of b is 0, and if I put b in place of this x minus b, these all terms will go to 0, and I get g dash of b is equal to 0. And from Rolle's theorem, we already know that g dash of c1 was 0. Now I will get there will exist c2 belonging in between b and c1 such that g double dash of c2 is equal to 0. You can observe the pattern, right? Now when I take the second derivative, I'll again put x equal to b, and I'll get g double dash of b equal to 0. And from Rolle's theorem, I got a constant c2 such that g double dash of c2 equal to 0. Now I can apply Rolle's theorem again, and I'll get another constant c3 such that g triple dash of c3 equal to 0. And I'll repeat the procedure till I get the n derivative. Let's see what we'll get at the n minus 1 derivative. X is equal to f n minus 1 of x minus f n minus 1 of b plus k times x minus b. Now if I substitute b in place of x, I get n minus 1 derivative of g at b is equal to 0. And also from, if I would have applied Rolle's theorem in the previous n minus 2 derivative to get another constant cn minus 1 equal to 0, where cn minus 1 would belong in between b and cn minus 2. Now I will apply Rolle's theorem again finally, and I get gn of cn is equal to 0, where cn will lie between b and cn minus 1. Now when I take the next derivative and put cn, I get k is equal to fn of cn. Also I wrote b comma cn minus 2. This doesn't mean that b is less than cn minus 2. Since the first point I took, which is x, is an arbitrary point, these points can lie anywhere. Yes, now from here we got k is equal to n derivative of f at cn, which will give us that f of x is equal to sigma r equal to 0 to n minus 1 fr, which is the r derivative of f and b, divided by r factorial into x minus b power r plus n derivative of f at cn divided by n factorial into x minus b whole power n. Now, since cn will lie between b and cn minus 1, which will also imply that cn will lie in between b and x. Generally, we define this as p n minus 1 of x, and we call this as the remainder term. This remainder also has a special name known as Lagrange remainder. Generally, when we write the Taylor expansion, the infinite series of e power x and all, this Lagrange remainder will go to 0. But sometimes when we apply Taylor expansion, we see that this term will become 0 and the Lagrange remainder will give us a finite value. And we think that there was a flaw in our Taylor expansion. For example, you can try writing the Taylor expansion of e power minus 1 by x square. You will apply that, you will see that each term will look like it was going to 0 when you are putting n x extending, when you take the limit extends to 0. It was because the Lagrange remainder was not converging to 0 even if n was tending to infinity. Since e power minus 1 by x square when x was tending to 0 was balancing it out. I hope everyone understood. Now let us move on to our next theorem, which is Darboux theorem. Again, we will be using the same definition. Define the function as such that it is continuous in closed interval a comma b. It is differentiable in open interval a comma b, where a comma b belong to R and b is greater than a without loss of generality. Consider two real numbers n comma n such that they belong in between a comma b, where f dash of n is less than k is less than f dash of n. Our claim is that there will exist a c belonging to n comma n such that f dash of c is equal to k. Now, you may say that this is just a straight up intermediate value theorem, but it's not. Your f dash of x need not be continuous always. Many of us think that when a function is given to be differentiable, its derivative will always be continuous, but it's not true. So let us see how this function, how the derivative will follow intermediate value theorem, even if it's not continuous. But before we do that, let us define a function g of x is equal to f of x minus kx. Since f of x is differentiable in a comma b and x is also a differentiable function, g of x can be differentiated. G dash of x is equal to f dash of x minus k. If I substitute n in place of x, I get g dash of n, and we know that this quantity is less than 0 from the given conditions. Similarly, I get g dash of m is equal to f dash of m minus k, which is greater than 0 from the initial conditions. Now, let's do one thing. Let's apply first principle of derivative at both these points. I can write limit x tends to n plus, which we got to be less than 0. Now, since there is a reason I took n plus instead of n, this will imply that there will exist a delta such that in this interval n and n plus delta, let's call it delta 1, where delta 1 is greater than 0, the function is strictly decreasing. And similarly, if I take limit x tends to n minus, which is greater than 0 from here. Now, again here I took m minus, which implies that there will exist a delta 2 such that in m minus delta 2 and m, the function is strictly increasing, where delta 2 is greater than 0. From these both equations, we can infer that the extreme point will strictly lie in between n and m. Let's say the point is C. C belongs to n comma m, such that h of c is extreme. And now Fermat theorem guarantees that at this point, since h of c is an extremum, the derivative must be 0. So now this will imply that g dash of c is equal to 0. If I put in c in this equation, I get f dash of c is equal to k, which was what we were supposed to prove in the Darboux theorem. Now if you notice properly, you can see that though the derivative might not be continuous, it can have discontinuities, it cannot have all types of discontinuities. So suppose if someone says that can you define a function whose derivative will have jump discontinuity, you can strictly say that there will exist no function whose derivative will have a jump discontinuity, because we see that the function is following intermediate value theorem. But what type of discontinuities it can have? It can have discontinuities like isolated point discontinuity. I hope you understood the significance of this theorem. We can end this video here. In the next video, we will solve some problems based on these theorems, which are of ISI and CMI style. Thank you. Take care. Goodbye.